And as mentioned there, I'm the team leader of soft robotics program in ACES. And at the same time, I'm in the grey side of university. I'm head of the school. Just following Roland's definition of dark side. I call it grey side. I'm head of the school.
You got a leg in each camp, like that can be uncomfortable.
So I'm the head of school of mechanical, materials, mechatronic, and biomedical engineering. So as of next year, we have biomedical engineering as well in our university. So I'm going to talk about soft sensors, soft strain sensors. Before I talk to them, I would like to take this opportunity to talk about the team I'm leading with a couple of people, and that's very relevant to the talks in the morning. I'm very motivated to present what we are aiming at and find some new networks, some new ideas to work together and to deliver more. So soft robotics is a new dimension to ACES. It's one of the applied teams. So our aim is to use these electromaterials, these novel smart materials, to use them as actuators, which are the primary building blocks of robotic systems, anything moving. So we have actuators, sensors as well, sensing. Of course, mechanisms. So you have to have some mechanisms which can convert energy from mechanical energy to amplify or to increase speed or to increase the power. So the idea is to develop some soft robotic systems and especially prosthetic devices. So before I move to the next slide, if you are leaving robotics, I mean robotics is defined, although there is no single definition people agreed on, it is the science and engineering of devices which can be reprogrammable, multi-purpose, multi-dimension devices which can connect sensing into action. So it has to sense and convert into action with some intelligence. So that's typical robotics. Soft robotics can be defined as the science and engineering of robots which are primarily made of soft materials and mainly monolithic structures. Monolith means one piece. I'm going to show you some examples here. I'd like to bring down some examples. Maybe I'll show you later. So we printed some hands and some fingers. You may gradually start touching them. Maybe I'll start from our visitors from somewhere else. That's another hand. Maybe I'll show this one and then I'll pass it to you. So the idea is to use soft materials so that the new robots can have a smooth interface with their physical environment better than their predecessors. The predecessors had to use force sensors to control the force between a robot and the environment. So the idea here is to tolerate inaccuracy because of the softness, but safety is also guaranteed. So that the idea is to use these materials to have a monolithic system which contains actuators, sensors, mechanisms, energy source, battery, electronics, such that, like our hand, like our biological counterpart. So in that regard, we are very excited to be in ACES because ACES is a truly multidisciplinary group. So here is one of our photos, and this is the hand we completely printed from low-cost polymers, and I can send that one around. And so our idea is, grand challenge is to develop a prosthetic hand or limb which is compatible with natural control. So we want it to be like we control. So you can feel the touch and then send back that touch to the user. You can feel it. When you close your eyes, you can understand what you are touching, what you are doing. So that's the dream, of course, not easy, but we believe we can get closer, one step closer, to realize the dream of realizing some prosthetic limbs compatible with natural control. So I'm going to tell you what we need. So that's our hand, maybe I just mentioned to you, and it will be lots of things, but that's our ultimate goal. Ultimate goal is to have this hand here, and the current prosthetic hands on the market are heavy, not user-friendly, consume a lot of power. I think they have 23 motors, and you have to house somewhere in your arm, in the user's arm, and 2/3 of the times, the users don't want to use it because it's not user-friendly, not acceptable, too heavy, and you have to carry it. So our aim is to have a soft one, lightweight, acceptable, plus sensors built in the fingers, in the palm, and then sending back those signals to the nerves or muscles, or to the nerves for feedback, and And using a signal from the muscles, that's why this morning I asked Wearable Chang, can we use your soft strain sensors put on the muscles to determine the extension and contraction in the muscles, like the EMG electrodes being used in the current prosthetic hands, to get a signal from the user, to understand user's intention, and then send this signal through something like this here, so reading something happening in the muscles or in the skin, and then controlling. Of course, the user is in the loop. He or she will see what they are handling, but at least if you can turn it on, and more importantly, getting a signal back to the user through neural interface. That's a big challenge. But we are lucky we have multidisciplinary programs. We have biosystems, we have people doing lots of research about interface with the cells, with the nerves, and 3D printing. We believe within the next 5 years we will be coming with a hand which we will call UOW hand. Seems to me we were a bit shy when we printed the hand. I was just showing you, maybe I'll show you this video. We saw many hands in around, but not a single piece printed at one go and including everything. So if I can show this video, I think that will be enough about the team I am representing, and then Gordon can give me more money. Okay? So that's one of our hands, and we are very careful not to do anything about the middle finger.
That's when you don't get the money, right?
So that is our finger. Also we build, so that's the hand. Also we do, of course, lots of fundamental research. We believe you need to use some scientific tools to make the best decision. So I should mention that Rahim Mutlu, he's here today. He did this work, as he's the first author of this paper, just accepted to this top robotics journal, Soft Robotics. Although it's a new journal, its impact factor is the highest. And he did significant amount of work in using finite element modeling to incorporate the non-linearities in the material and in the deflection, because this deflection is not small. And then to optimize the configuration of this real finger, and then he put 3 fingers together, this one. And by the way, these are my fingers, these ones. The ones holding the gripper, and this is my apple for lunch. So this was. So this is the hand we also printed, and we did this one. And also what we did, another project done here, we built a 3-finger gripper here, and we put at the end of an ABB robot in our labs on the main campus to handle a spherical object like a grapefruit. So you just have your lunch. I don't think anybody will feel hungry. So the idea is to use this one in agricultural applications. So because of the softness in the fingers, and it doesn't damage this agricultural product. The next one is about handling a capsicum. I mean, is that one? And this work was done by an undergraduate student, Taylor Kenty, in his undergraduate thesis. And we just submitted this one to Soft Robotics, and we did a lot of modeling work, evaluation work to optimize these chambers. I mean, here you may have something strange. Those fingers do not collapse under their weight. So when they are vertical, they are straight. So in there we use some very simple ideas to put a layer of something, because we haven't published it yet. And when we apply a small input, it deflects. And before that one, it is straight. So we engineers, we made some small changes. This kind of design decisions, as the speakers this morning mentioned, design is important, coming with some new ideas. So this is what we have been doing as in soft robotics. So our aim is to use new materials, soft materials, to establish new novel actuation and sensing concepts, and then translate those ones into prosthetic devices, in particular to a prosthetic hand. And let's return to my main talk. My topic of my main talk now today is about soft strain sensors. So as part of this research, we are also looking for some sensors which we can print simultaneously on the finger, and when these bands, I'm going to show you a video at the end of my talk, to get information about the bending and using these bending signals to estimate its shape. And then later, we got some other ideas in between here to measure the compression force here, and from here to estimate the grasping force. So the idea is to have sensing and actuation in a nice unit. So that's our finger with the sensor printed, and that's working. So here are the soft sensors. So these are the technologies like to measure pressure. And this is from the sources and strain sensors. I'm going to talk about this one. You can apply a mechanical strain, and that generates an electrical signal. And here you can use two conversion mechanisms, either changing resistance or changing capacitance. You can use it. I will tell you more in a second. Another one is to measure curvature, just bending like in our fingers. Another one is shear. So these are the mechanisms, technologies in soft sensing. And these are some applications, wearable tactile keypad. Maybe I shouldn't show these videos after I saw a couple of presentations this morning. Then I said, look, everything's almost done. So they showed brilliant results from their research fields. I'm very excited to talk to them more and to establish some new networks. So motion sensing suite, that's very important. Wearable robotics or assistive devices. I think that's an area in wearable assistive devices. Active soft orthotic to measure pressure to help people to prevent their fall. Of course, joint angle measurements for prosthetic hands. But these are the conventional ones based on hard components using tendon systems, pulley systems, etc. But these are the ones we saw them this morning. There are many. So this is the one we are targeting. Of course, you can use shear for grasping or human-machine interface. That's very important. And here are some applications for wearable sensors. I think, as mentioned this morning, and that makes my job very easy. It can be used to measure sensor and pressure as sensor. They can be used in many areas like voice monitoring, as demonstrated, heart pulse monitoring, wound healing, mapping body temperature, etc. Body temperature. So these are the typical applications. Again, it's coming to the sensor, how well the sensor design, how sensitive it is, how flexible, how stretchable, as I tried to ask. It should be compatible with the skin of everybody. So it should have a lower modulus of elasticity. This is some information about wearable sensors, and in general they have a nanomaterial and a flexible and stretchable elastomers. So you know nanomaterials better than me, carbon black, carbon paste, carbon nanotube, lots of things can be used. And here you can use EcoFlex, everybody mentioned of that. PDMS, VHP 410, you can use this one even. And so there are some different sensing principles. These are the new ones, like tunneling effects, using electron tunneling. Another one is crack propagation in thin films. This connection between overlapping nanomaterials. These are some new mechanisms. But when it comes to simplicity and effectiveness of the solution, simple is always better, as you will agree with me. So in that regard, resistive strain sensors and capacitive strain sensors are the most popular ones. They don't require too much hardware and software, and the sensor itself here is a variable resistor, and here you've got a capacitor to handle. As I just mentioned here, capacitive ones have a high linearity. They are linear. Their stretchability is very good. Their hysteresis is low, but their sensitivity is low. Sensitivity means their gauge factor is usually less than 1, which is not enough for some application. Resistive ones have some advantages, like high sensitivity, stretchability, but their hysteresis and nonlinearity are the problem. So knowing these ones, we did some work in our group recently, in parallel to what we are doing in the actuation and 3D printing of the hand. So what we did, so these are the last 2 publications we had this year. One was just published in this journal, having an elastomeric strain sensor and filling up a PDMS-like substrate with a conductive fluid. Okay, very simple idea, well known. And then to test it and compare with some different conductive fluids and substrate, and comparing with a commercial stretchable sensor. So that was our aim, to determine what sensor will go well with our fingers. And we found that this does not work well, but we published it. That was the good thing. So sometimes you publish something which may not be useful. So we found that the compliance of this elastomer base was higher than the fingers when it peeled off after 10 cycles. So that was a very simple lesson. And I'm just looking at my watch. I will finish in 10 minutes. So this is the sensor. We did it like a classical strain gauge. And as everybody knows, strain is less than 10% for them. But for these ones, it's quite high. Very simple idea. In fabrication, again, it's very primitive. I don't want to even show you too much. We use another silicon-based material from Japan called Shin-Etsu. They're trying to find different materials as a substrate to see which one gave us better hysteresis and non-linearities in terms of this performance one. So it's just simple things, we use etching, all these. I don't think there's anything advanced here, but these are the dimensions of our sensor. And we use these two conductive liquids, okay? And P.PSS, I'm sure this community knows this acronym better than me. If you ask me, I can't pass the exam. So P.PSS, it's a conductive fluid. Of course, carbon black diluted, and then we use these bases to make 3 groups of sensors with this dimension. So what we did, different than characterization, because we are engineers, we want to characterize them near real conditions, such as linearity, how linearly changes, hysteresis, some people do it, resolution, response time, how fast it goes and comes back, returns to the neutral position, etc. And also we try to look at their reliability and robustness. So this is something to do with the repeatability, of course, and these were our criteria to evaluate this sensor. So we built something simple like this in our lab, and we just apply some mechanical strain, very simple. We have a variable resistor, which is the sensor itself. That's our resistor load, and using this simple setup, and we managed to get some results with these 3 combinations, and we found that the gauge factor is around the gauge factor of the classical strain gauges, and again, there is nothing advanced here, and they're quite linear, and here is the resistance, and this is the change in resistance, that's our strain, so this slope is our gauge factor, and quite consistent hysteresis. Some of them, I think this one looks better. There is a bit of, not quite hysteresis, it's quite repeatable. Loading, unloading, you can see this is not good actually, these ones are better. The return path is the same as the forward path. So also one thing we look at was after we strain them and leave them to go to 0 strain, so there is some reading in their resistance. So it takes some time to go to 0. That was another problem we identified. So resolution was below 1% in all of them. And the transient one we were interested in, we were interested in the transient response, how fast they go and come back. And here we got the EcoFlex one, and this is the Shin-Etsu one. You see Shin-Etsu is slower than the EcoFlex. Now this explains why EcoFlex is a popular polymeric substrate in many publications. So these are some pros and cons. And so fast, low fabrication cost, high strains, still okay. Linear relation is wrong. Resolution is below 1%, small time constant, these are all very good. But fabrication is tedious. And also we found that the conducting fluid disappears over the time. Seems to be there are some problems there. And we also compared with some commercial ones. And this is from New Zealand using some dielectric materials and some conductive electrodes on both sides. And also we did some work on this commercial one supplied by this company. We found that this is its performance is well below what we did, and this is ours, and this is the commercial one, and larger hysteresis, and its resolution is not good. And more importantly, its settling time is 200 minutes. So it takes ages to come back. So that was one problem we found in this commercial one. So the application, I just told you, the finger we have, and we just look at that, and this is our experimental setup. Initially, we put them on the fingers, and it didn't quite work. So our idea is to get a model, mathematical model between resistances coming from 3 joints, Okay, so readings, and this is our measurements of the angles. We measure the angles using a vision camera system. We put some dots on the joints and measure those ones, and that's our model. And we found that our model can accurately estimate, and there's a linear relationship between bending angle and the resistance. Of course, we are going to do the position control. That's work in progress. And this is another work in progress. This video, I will just show you recently, we made the soft ones. And this is real time, by the way. There is no fast or anything, so we use this experimental setup. You see here, these are the change in resistance we measure simultaneously from 3 joints. So our idea is to identify the models for these fingers without using any external sensors, build in and estimate the configuration of the finger. So these are some challenges after I listened to this morning, and this is in line with a recent publication from Advanced Functional Materials. In there they said there is a challenge to have highly stretchable, highly sensitive wearable sensors. But this morning some colleagues presented some results. Stretchable is not a problem. Sensitivity, maybe gauge factor is not 50, maybe below 50. So we robotics people think this is a challenge. If not, we can do it, but I think this is something we need to look at. And that's another challenge, measuring strains in multi-planes, not only one direction, can you measure from the other dimension simultaneously. Measuring strain here and here, if you've got 2 planes, that's a challenge. Packaging, I think this is something we'll agree with that one. When we test in the lab, we don't care about the size of the sensor, the power they require, number of cables, what devices we are using for recording. But when it comes to a real application, it has to be low footprint, it has to be compact, it has to be small, it has to be packageable. So in that regard, putting everything together, including power source, signal processing, recording, communication, data storage, etc., is a big challenge. I guess speakers outside Wollongong will agree with that one. Packaging is a challenge. Another thing I was asking a question about, compatibility, compliance of the sensor should be lower than the surface they're going to be done. So here I put a question all the time. As you see here, I mean, these are something I prepared before I came this morning. See, progress in soft materials will make a big difference, as most of you mentioned this morning. So we need to put our strengths together, and I like this equation. 0.5 plus 0.5 is always greater than 1. So it means synergy. So if we put our strengths together, I believe we can solve some of the challenges. We engineers can provide some feedback with you, as we are doing in ACES. And as many people said before, we need to work together to solve these problems. Okay, so this is the world without engineers, of course. And I got this one from somewhere, but I can't think of the world without scientists, without material scientists. So we need you to make these ropes. Okay, so this is the people, these are some people I want to thank. Şölen Yıldız, she did the sensor work, Ryan helped as well. Vitor, these 3 people significantly contributed to our strain sensor work. Of course, many people, students, research fellows. I didn't do much, I just delivered this talk. And of course, for funding, ARC, University of Wollongong, and without them, we wouldn't do it. So, thank you.
Any questions?
Just thinking about your 3D soft figures.
Yeah.
Their durability, like how long do they last? And I was thinking about with the fruit, you know, if you had a bad batch of fruit that was contaminated with some fungus, you know, the decontamination, will they survive the decontamination process to get rid of, you know, bugs and stuff like that?
Good questions. I mean, if I start with the first one, I mean, life-wise, we haven't tried. I mean, we made lots of thousands of cycles with that finger in the last video, and we didn't see any visible cracks or separations of fatigue. So, of course, that's not our final finger. We got another configuration, we haven't published it yet, which will increase their load carrying capability while still soft. Can we increase their strength, especially in this configuration when carrying the load? So we are not there yet in terms of saying that life is this. For the second question, again, this is something we did just to show where it can be used. Again, I'm sure you can cover the surface of these fingers with something, maybe with some sensors, with detecting the smell. Seems to me there are some wonderful sensors around, chemical sensors to detect smell, which is the smell of some fruits or vegetables, and you simply drop them and put in another box, I guess. So we are not there yet, but these are very relevant. So the reason I'm showing this one, look, I believe if we work with the application people, with the practitioners who will be using this one, we can tailor our design according to their needs. That is the message from us. Especially would like to interact with the industry to understand their problems better. And I believe if we understand the problems better, we can find a solution. Usually we make decisions in isolation and end up with some unrealistic assumptions. So I hope some people here will take this message and will work with it. Thank you. You haven't finished yet.
Answer wasn't accurate.
Was it too much?
Any more questions?
No.
I'll ask one quick one.
Sure. We have 2 minutes still.
Have you integrated any feedback between the sensing and the actuation yet?
No, but we are controlling, in the previous slides, we are doing this one. We are getting the angle back to control the position of the finger. So if you take this one, it goes to the actuator. So that's happening. So we are currently drafting a paper using this control system. And then extend this one to the hand, of course. This is for the finger.
Right. Okay. Can we thank Gursel?